Hey, good morning, everyone. How are you feeling? Are you ready? You're almost reaching the midpoint of the summer school. Midday, Wednesday will be midpoint. I hope you can keep enthusiastic and motivated for what remains of the summer school. So this morning, I have the pleasure to co-host this session with Davide Consoli, which I hope you know from OpenGeoHub. This is a bit of a different session. It's, let's say, a bit of marketing. We are promoting this idea of discrete global grid systems. I say marketing, but then the name, it twists your tongue a little bit. Someday we have to fix this. In any case, what I want you to go home after this session with is an idea of what are discrete global grid systems and what you can do at present with them, and maybe what you will be able to do with this concept in the future. So let's see, who has ever heard of discrete global grid systems before? Okay, Daniel has. All right, yeah. So good. I think this is the audience. People that never heard of this before, right? Very good. Okay, so why are we here today? Yeah, can you read this? Can you read it? So this is a bit of a joke, you know. So, some people still think that the Earth is flat somehow, right? And of course, if you have a lot of money, it's much easier to think of the Earth as a flat domain, whatever. Yeah, but for us, scientists, mere mortals, that's not the case. The Earth is not flat at all. It's this wonderful blue marble. When the astronauts from the Apollo mission, they went to the moon and they saw this, yeah, this blue marble there in the distance. So I'm so far away from home, will I ever come back? And it was beautiful, they say, right? And we live in this beautiful place, but it's spherical, ellipsoidal, whatever we want. It's for sure not flat. And this creates a lot of issues, right? And you probably studied map projections, the distortions associated with map projections. And the problem is that if you are working in a large enough domain, continental scale, or even the scale of a large country such as the United States, and you want to do things such as environmental sampling, these kind of distortions, they are really, really a burden on you. You know, you cannot easily create, for instance, a regular sampling grid for a large area. This that you see here are the 19 UTM zones that are defined for the United States alone. And we are not even seeing Alaska and Hawaii, right? So way back in the late 1980s, the EPA in the United States was trying to develop an environmental modeling network for the country. And they were facing this exact same problem. How are we going to do this in such a large country? So they teamed up with the University of South Oregon, and sometime in the early 90s, they started exploring this idea of using different methods to project the Earth on a flat surface. And one of the things they notice is this amazing shape, the football. And those folks, well, most of you are very young people, but back in the 80s and in the 70s, you've just seen images of football matches from that time. Footballs would look like this, right? It's the composition of hexagons and pentagons. And this is actually a particular shape called the truncated icosahedron. And what those early researchers in the US understood is that they could actually enclose the contiguous United States in a single hexagon in one of these footballs, right? And then if you have this flat hexagon, from there you can build a regular monitoring network. So they kept exploring this and came to the conclusion that using things such as the platonic solids, so the solids with a number of equal shape spaces, you have somewhat directly ways of subdividing these faces into ever more refined grids. Okay, and we are here. We are making the step to the discretization of space. All right. So I will come back to this a bit later. And then there is a major step that happens here. Those folks in the University of South Oregon and the EPA, they team up with John Snyder. Who here has heard of John Snyder? Okay. The usual suspects. So John Snyder was probably the greatest cartographer of the 20th century. He wrote 2 or 3 reference books on map projections, and he was one of the first people in the world to actually code map projections. That code, as far as I know, is lost, but his books still have small images, small figures like this one that were produced by code that John Snyder did way back. And John Snyder joined this little club around the monitoring network, and he developed a map projection equal area for the platonic solids. Okay, so there you gain a method to subdivide in an equal area paradigm this kind of solids. Okay, and this is what makes everything start moving. So they come to this idea of the Snyder equal area grids, and they start working with the icosahedron. The icosahedron is a solid that has 20 faces, and the faces are equilateral triangles. And then this can be subdivided continuously, and you start having discretizations of the globe like this. Okay. And see another slide. So this is the icosahedron, okay, a bit of a 3D plot of this solid, and some of the ways that you can subdivide it, especially with hexagons. So it's the hexagons suit very well. You never get actual squares in these kind of subdivisions because the squares are just way too cumbersome for the spherical surfaces. So usually the subdivisions are made either with triangles or hexagons. You have also other options. I will see a bit more later. Okay, so we're coming now to the late 90s, and that's when this idea of discrete global grid system comes up. And these are the advantages, okay? So no more distortions of map projections, right? You are using a single paradigm for the whole globe, and you achieve relatively easily the equal area discretization. Doing this, you are automatically inducing important improvements in efficiency because you reduce storage and memory. So if you want to store a grid of the whole world in a Plat Carré projection, you're storing far more cells or pixels than you would need to, okay, because it's not equal area. Once you apply a paradigm like this, you just use as many cells as you need, okay? Also, you have a single system for the whole Earth. Doesn't matter if it's Antarctica, if it's India, if it's Alaska, you're using always the same system, and the system is scalable, okay? You can always refine your grid further. Okay, so a bit more of history. 2003, there is a gentleman working at the South Oregon University called Kevin Sarr, and he codes the first software for this kind of grids. It's called DigiGrid. The first version came out in 2003. That was about the time that Kevin was finishing his PhD. And here are some beautiful plots from grids created with DigiGrid now well over 20 years ago. 2006, I myself created these pictures in a small conference paper. So in 2006, I was able to compile and run DigiGrid on Windows. I have no idea how. No idea how. I didn't use Windows for much longer, but it was enough at least to create the grids. You couldn't do much more than this to create the grids, and these are plotted, I think, with Google Earth, Google Earth, yeah, indeed. Google Earth already existing at this time, and then, yeah, this was a lot of fun, but still not that useful yet. But yeah, you have already software. And research continues, and especially Kevin Sarr continues producing high quality scientific content. And one of the things that Kevin starts promoting around this time is the fact that a discrete global grid system is actually a reference system. It not only discretizes space, but it allows you to locate anything in the the spherical domain, the ellipsoidal domain, with perfect accuracy. Okay, and we'll see a little bit more how this works, but basically it's just an indexing mechanism. If you have a way to index every cell in the grid, you can locate anything with any kind of precision you want. You continue refining the grid, and as long as your indexing mechanism works, you can always uniquely identify that place. So 2009, we have the industry coming along. So this software, Pixis, is already in the market by this time. It was developed in Canada. Probably the main person behind this is a gentleman called Perry Patterson. Pixis was not a success. It was not a commercial success. The company, I think, doesn't even exist or sold or whatever. And well, I'm not an entrepreneur, so I cannot tell you exactly why the company didn't succeed. One thing that is important is that Pixis was a closed source project. So it was maybe a product of its time. So it was there were expectations of income, etc., that probably were not met, and also it might have been too early for a concept like this to prevail. But Pixis did a lot of work. Pixis is the name of the software and the company did a lot of work, a lot of good work, and they proved that indeed this could work, that you could do a commercial grade product on this paradigm. And then in 2015, we have something very interesting happen. Uber, the not car sharing, but car hailing company in the US, releases a library called H3. It's open source, and it basically implements a discrete global grid system that is meant for their work related with billing and ride hauling, etc. It also brings a novel way of subdividing, of refining the grid, so you can have a little bit of an idea. So you start with this big hexagon, and then you refine it in 7 hexagons with a little rotation, and then on and on. Okay, and clearly it is a reference system. It's I don't know if it was the first implementation of a DGGS as a reference system, one of the earliest. And it's open source, and they put it out, and they have bindings for JavaScript. They have bindings, I don't know if for R, for R there wasn't, but maybe for Python was also very early, and suddenly everyone could use this, okay? There is only one catch, is that Uber did this DGGS without an equal area projection, so those cells, they can be quite different in size, even within the same refinement level. Okay, so this means that it might not apply to all applications, but it's a very interesting library infrastructure to have. And then in 2017, we start having the standards bubbling up. The OGC publishes. Does everyone know here what is the OGC? No, Open Geospatial Consortium. So it's a consortium of companies, scientists, and public institutions that set standards, especially of determining the ways that we share data, geospatial data. Okay, so things such as the APIs, the OGC APIs, the WMSs, the WFSs from decades ago. This was all specified by the OGC. The OGC had this specification in 2017. It's called the meta standard. I don't know how useful it is, to speak frankly, but it was a good exercise and brought together people from different contexts. Perry Patterson was involved. There were people from Esri, people from universities in China and Europe, in Canada. And I think it was also a moment of having people together thinking. And then recent years, of course, with the software becoming better and more software becoming available, there is an explosion of work. This is something I did already, I don't know, a few months ago, maybe 5 or 6 months ago. And if in Google Scholar you do a search for discrete global grid system and you get 250,000 results, okay? So of course, this is modern scientific publishing. How many of those works are really relevant, I don't know. But this has really made it into the scientific domain. Okay, so this is the story so far. Okay, we have, since the beginning of this year, we have more concrete standards from the UGC, and this standard specifies an API to interact with services that provide data in this paradigm. So it's part 1, part 2 will be coming and specifies a few more things, but here this standard defines a lot of concepts that are important, like how can you interact with one of the systems to, for instance, to locate things, to retrieve data, etc. How are we on time? We are good. Okay, so the second half of this session, we're going to see a little bit of hands-on with Davide. And before we get to that, I'm just going to recap here a little bit the essential concepts. How do you build a discrete global grid system? So first of all, you start with a solid. Most cases, it's a platonic solid. The most used are the icosahedron or the dodecahedron. And yeah, because the more faces you have, the more I think I wrote heterogeneity, but should be homogeneity. Sorry for that. So you have the cells become more homogeneous. Okay, but you can use other solids, and people have used, for instance, the octahedron also. And the idea is that you're projecting your spherical surface into this solid. Okay, so just imagine that the solid is there embedded within the sphere, and you project back and forth to the faces of the solid. Okay, so that's where you start. Then you need a map projection, right? You need to have a mathematical function that does that projection from the curved surface into the faces of the solid. Okay, Snyder equal area. It's quite popular, but more recently there's a projection that does pretty much the same, called the vertex-oriented great circle. Yeah, its projections always have these weird names before someone abbreviates them with the name of the author. Also equal area. And then we have the gnomonic projection. This is what Uber uses. But essentially, any kind of projection is applicable, and then this determines exactly how the cells of the grid are shaped, and whether they are equal area or they are equal in shape, or if you're more interested in the distance. I think that was more the concerns with Uber. Yes, Edzer.
If I could go back one slide.
I can.
So you mentioned that the icosahedron.
Yes. Icosahedron
was used most. Right?
Yes.
I wanted to sort of go a little bit in that argument. It's a little like used by whom. So if you think about the number of independent implementations, then yeah, there's maybe 4 of them and not the cube. If you think the number of users daily use of software, you shouldn't rather skip S2 geometry, which is the Google provided open source library that is cube-based and that basically empowers all Google products. So if you think of the number of users using actually in the background some technology, I would dispute your argument.
Right.
More.
So the question here of these solids, which is most used in terms of implementation or most used in terms of users, right? So, and the answer is pointing here that Google, the S2 global grid from Google uses a cube. And whether isn't that more used because it has more users? Actually, I don't know, because H3 is also quite popular at the moment, or it has been in the past the past years, ever since it was published. So I don't have a feeling for that. But when I say most used is in terms of the implementation. So every now and then someone comes up with a new system. And those that are showing up recently, they are based either on the icosahedron or the dodecahedron. So, but others are possible for sure. And in terms of users, this I don't have really the feeling to say. But you could be right for sure. All right.
Google Maps.
We
use Google Maps. We use Google.
Yeah. Yeah, indeed, and that's also the point, is that many people are using this without knowing they are using it, right? Yeah, it's some software running in the background and they don't know, right? Here, I think, yeah, here is important to consider this in the scope of a data scientist, right, or a geoinformatician that wants to do sophisticated stuff with this. That would be the scope. Yeah. Okay, so let me continue.
Well, following that argument,
yes,
all our users working on geodetic data are using S2 geometry in the background.
Okay, I didn't know that. So there is
users, I don't know.
Okay, I was pointing out. I repeat that for the recording. Adler is pointing out that S2 users, no, SF users in R, they are in the background using S2 from Google. Okay, so that's, I didn't know that. That's very relevant. That's already a very large number of users. Yeah. Okay, thank you, Edzer. All right. Okay, so platonic solid, you shoot a solid, a map projection, and then a way to subdivide the faces of that solid. Okay, so Google S2 uses the hexahedron, the cube, because then they can use this. They can do this rhombic squares. With the icosahedron, with the dodecahedron, it's more common to use hexagons or triangles in schemes similar to the ones you see here, but you can also do it with this kind of diamond shapes, okay? And then there is this concept of aperture. I don't want to burden you so much with the jargon, but the aperture determines how fast the grid refines. If I refine a larger cell in 3 smaller cells, in 4 smaller cells, in 7, so if it's a higher number, this gets very fast to very small cells, okay? And it's especially relevant with the hexagons that have different ways to refine. And then a very important element in all this is the indexing scheme. It's the mechanism, a mathematical function, a procedure that provides for each of the cells a unique identifier. I hope this is visible here with these hexagons. So what I wanted to notice is that in this case, we have a hierarchical indexing. So there is this red hexagon here that you don't even see completely. You only see 3 edges of it. And this is indexed with the number 0. And then we have, so 1 digit. And then we have the blue hexagons, and they are being indexed with things such as 0, 3, 0, 1, 0, 2, etc. 2 digits. And then you go down to the orange, and you get 3 digits to index each cell, right? So this is the kind of mechanism that is used, and it's hierarchical. And as you can see, again, for instance, if you focus here on the 0, 0 blue hexagon, you can see that all the orange hexagons, their index starts with 0, 0. So my identifier also identifies who is my parent, okay? So this is one of the schemes. This is, for instance, the way that H3 does it. And other indexing schemes, for instance, DigiGrid now recently have things like this. But that's the concept, and that's why we get to this reference system, okay? And if I want to refine further, if I want to get to very, very small cells, I just keep adding bits to my identifier, right? And if you think of it, this is not very different from lat long. I can say 23 degrees north or 52 degrees north, 9 degrees west, but that is identifying very large areas. Yeah, I'm talking of degrees. Then if I go to minutes and seconds, I'm identifying an ever smaller area, right? So this works exactly the same. Good. Okay, so let's see, how are we with the time? Halfway through. Yeah, so now let's just move on to Davide, see the hands on, and then we can open a little bit for questions, right? I hope this is still making sense. I see some very, very nice faces out there. It should be fun. Davide, please.
Thanks. So this is a QR code to Google Colab.
So maybe I sit down.
I let you scan it, but I mean, it's quite basic things only to show something applied. Do you scan? I still see some phones. Okay. Well, if you already scan, what you can do is to make a copy of the Google Colab. So you go on File, make a copy, because otherwise you cannot edit it, of course. And 1, 2 phones. Okay.
Yeah, Daniel is following on the phone.
That's next level.
It's
Okay. See one more phone. Good. Then what you should get is something like this. And what I was trying to explain is, if you go to File here, you can save it as a copy on. You have different options, for instance, Google Drive. And once you open it there, you can execute the cells. Otherwise, it will complain because of right uses. But yeah, this will be based on DGGL. I don't really suggest you to dig in the code, because it's written in EC, right?
EC, yes.
So this library we are working with, it's quite well organized. I cannot even find it.
DGGL.
And okay. But substantially, it's a modified version of C, and it compiles quite well. There were a lot of effort made to make it quite compatible with different environments. And indeed, if you install it on Colab, it does quite smoothly. It takes only a few seconds. And this library, we are going to use it through Bash interface, but also as some Python API and other interfaces. And what we are going to work on is on hexagons. And as Luis already explained, we have the icosahedral Snyder equal area projection. And this is hexagon with aperture 3. So you can see that if you consider the blue hexagons, within each area there are 3 children cells. So half, 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 and one in the center. One characteristic of hexagons is that for none of the available apertures, the parent cell matches perfectly with the children. That's why I'm not a super fan of hexagons, but they have other important properties. And yeah, as Luis said, hexagons are kind of spread in the GIS community, and maybe not in user terms, but that's also the stereotypical association. But we should not associate with hexagons and the GIS. There are other alternatives. But yeah, as a first comment, just to see some details on what we are showing. So we have this acronym. I stands for icosahedron, S Snyder, E equal area, 3 is the aperture, H is the hexagon. And the level shows a summary of, for instance, for each level of resolution, what would be the area of each cell, how many cells are in total. And just to refresh again the terminology, here level is the resolution. So higher the level, smaller the cells. And if we check level 0, only means that we are working on the simple icosahedron and the whole Earth projection on it. If we go to final resolution, as you can see, the area is quite smaller. And what do we do with this grid? The easiest operation that we want to do, for instance, is to have a point in lat long, and I want to know to which cell these points belong to. So, for instance, I put latitude 3, longitude -70, and I get, okay, the zone ID for level 0 is this one, the centroids, the neighbors of the cell. So, and this is in EPSG for 3 to 6 and lat long. So these are the most basic operations.
So this is here. This is the
bounding box.
The bounding.
Yeah.
Okay.
So these are the vertices of the cell. Also means that it's one of the pentagonals.
Yeah.
And what's next? Another application can be, okay, I have a bounding box. I want to know which cells falls into this bounding box. And this can be done in this way. And you can see this very cryptic indicization, but this uniquely identify where on Earth you are based on the orientation of the icosahedron. And to get some more insight of and see something more understandable, we can export the grids as a GeoJSON. So you can just create the grid and put the file in a GeoJSON. You should get it here in the file browser. I did this for 3 different resolutions. So 4 is the coarser, 5 a bit finer, and 6 the finest here. And these you can directly put in QGIS. Let's zoom out a bit. So you just drag and drop. Then let me just redo it at least for once. One of them, let's say level 4. So when you drop it, you get it like this. And if you change the symbology and just put some contour lines, then you should get something more interpretable, because then we can see what's inside. And this is projected in EPSG for 3 to 6. Are you familiar with QGIS? I guess after 2 days of summer school, you should have seen this already. And this means that this projection is not equal area, and you can see the deformation of the hexagons. But in reality, what these hexagons are equal area on Earth, and that's why they're actually distorted, because in for 3 to 6, the distortion is higher in the poles. And if we zoom in a bit, okay, you can see with 3 different colors, I specify different resolution levels. So you see the green one that is level 4 is the coarser, the black one that is level 5, and blue one that is level 6 And you can see, as showed before, that the aperture is 3, so the area of each children is 3 times smaller. And another interesting thing is, since we are in a icosahedral as initial shape, there are some cuspids, right? Are they called? For instance, here you can see that this geometry is not perfectly flat here.
Yeah.
And
so this is an artifact of the projection, of the Snyder projection.
That is actually what slice and dice tries to.
Yeah, and then the slice and dice projection makes this a little bit better. Right?
Yeah. But nevertheless, the area is maintained. It's just a geometrical deformation in specific points.
Davide, since we have time, maybe you could show 1 or 2 of these grids on geojson.io.
Okay.
So if you open there a tab. Does anyone knows of this website, geojson.io?
I don't.
Yeah. Okay. And you just need to load.
Drag and drop.
Yeah, you can try drag and drop. Why not?
Let's take the finals.
Now, can you try to drag and drop to? Here, open.
Oh no, it actually worked.
It worked. Okay. So, but we are not seeing it. Now we see it. Yeah. It was not refreshing immediately. If you try to.
Maybe I should have used the other.
So here you can see that. Yeah. So since we are using the icosahedron and the Snyder projection, which is equal area, these cells they are very similar in area. You cannot do equal area on perfect equal area on this curved surface or on any curved surface, but this is very close to be equal area all across the globe. And then if you use a different projection, then they are not as equal area, but they may have other properties. Then maybe they are the centers are equidistant, for instance, right? And yeah, so then in QGIS, what we see is this distortion because there is the flat carrier projection applied there on the fly.
Yeah.
So maybe now we can do an identify. I think, I don't know, follow your program.
Yeah, no, or we can also show another projection as we checked before. If we check, for instance, the homolocene land projection, that is sort of equal area.
It is equal area.
Yeah, right. I mean, you can see that in this case, the hexagons are uniform. However, there are still the cuts on the truncation.
So most of this software, like QGIS, has a hard time handling with interruptions in map projections, right? And sometimes it's just the 180 degrees projection, what people call the Hauer meridian. But in general, because these softwares, they are meant to work in the Cartesian space. And so people are usually not concerned with this kind of issues. You see this also, for instance, if you would plot this in grass, you would see similar artifacts. Okay, so that's why then we can use things such as geojson.io or Marble. Who here knows about Marble? No? Marble is a globe. It's an open source globe, so easy to install.
Yeah. So now that we have a bit more clear what.
So maybe you do an identify to show on QGIS.
Yeah, you mean to
do an identify
to find the index? Yeah, I think I would do.
Okay.
With the points here.
All right.
Yeah. So I did add some more real case examples. Let's say here we have a bunch of points for land cover, and I load them as parquet. I extract the geometry, And are you familiar with Pythons or are more refined with that?
Let's assume that.
Yeah. But so essentially, this is just the data frame. I sample 4 points for which I have lat and long, and I use GeoPandas to get them as geometry. And the same I did with 2 of the grids that we just showed in QGIS and GeoJSON.io. In this case, the grids are polygons and not points. And what we want to do is a spatial joint, or overlay, depends a bit on the context, but substantially indeed to find to which polygon the points belong to, and the polygon is associated with a univoc cell ID. And is quite straightforward with GeoPanda, so just do a spatial joint, and you can see the output. So for these 4 points, we have here the zone ID specified, and same goes in this case, but this is for level 5, this is for level 6. And you can also export that as a geo package and put it in QGIS.
And it will join on the geometry and not on the cell ID, right?
It will join on the geometry, and from the geometry, you derive the cell ID. So, for instance, for these points, that might be different from the one I just showed because I sampled without seeding. So you can see that this point belongs to this wider cell here. And if I take this, and I select the correct one,
Yeah, you want level
yes.
4. Yeah.
Okay. So for this level, the zone ID is C030D. But you can see that in this level, the 2 points are falling in the same cell ID. So it means that to distinguish that, I need a final resolution. And you can go on level 6. And here, in this case, the 2 points fall in different cells. And you can indeed also identify with maybe.
Yeah, you have to select.
Oh, yeah, you're right.
We can see you don't work so much with QGIS.
No, I actually do. I thought it was the selection there. And in this case, you get the lower level cell ID. But of course, it's not scalable to do it in QGIS, and you can simply do it with the GeoJSON, the GeoPanda interface. And yeah, that's pretty much it.
Right.
I don't know if you want to add something or
yeah, this exercise. So this that Davide showed us is something that I did many times. Basically, we are doing a spatial stratification. Okay, and when you have global data, when you're working with a large in a large region, I used a lot this kind of grids to stratify my data, for instance, to do splitting, etc. And that is for me one obvious use of this software for a data scientist or for a spatial data scientist, if that thing exists. Okay, so we are good on time. There are still a few slides in the end, but let's see. Do you have any comments or reactions at this point or questions? Let's start with Daniel, then answer.
So you told us about how to join tables, like which point is in a certain area and things like this.
Yeah.
In PostGIS, we have this. It's not using a DGGS, right? Like there's points in a polygon, and you need to check longitude and latitude of every point to see if a point contains a polygon. But in UH3, for instance, if we encode the zones and the subzones, like we put the parent name inside the ID, we can also make special joins.
Yeah.
So we can, I mean, we use this in SF, for instance, where DGGS helps us to work with spatial data, right? How do you do the joins?
Well, the thing is that the question is sort of what do you use the discrete global grid for, right? So if you want to use geometries with their exact coordinates, at best you use it as a spatial index, right? So you look at some say in which cells is this polygon, which cell is that polygon, do they intersect or not, and you can discard it. And that is very fast, right? But if you want to compute an intersection, you want to have the exact intersection, not an approximate intersection of a number of cells, right? So that is a bit the trade-off. You sort of you're completely going to work with polygons or areas that are composed of these hexagons or S2 cells, or you want to stick to your real precise coordinates as they are, right? For exact coordinates. That is the trade-off, and in S2 you can go one way or the other. And the way with the sort of seeing polygons as collections of cells, we still have to further implement to use that speed game.
So sometimes the DGS features help us also in do this computations.
Yes. Right, they're an index, right? They use a spatial index.
I like the.
So that is the, as opposed to the quad tree of the SRP,
like quad tree.
Which is used to plot the play.
I believe that PostGIS still uses quad tree, but maybe this with quad tree. A quad tree just divides in smaller and smaller squares. That's my understanding, but I'm not sure.
It uses the spatial curve and some coding system. Numbers.
All right.
But yeah, you can see it.
So you have another comment, Answer?
So the examples you show are really vector data, right? You use the polygon stuff. Looking at the polygons and doing polygon geometry.
Yeah.
Right. I wonder because there are really large data sets. The really large data sets are the things like high resolution images. Sentinel-2 is in regular grids on UTM zones.
Yeah.
Could we use that data? Can we use that data in discrete global grid representation? Because that would make things fly, right? So as opposed to using it just as a coarse index and finding whether things overlap or not.
Yeah, so 2 answers to that question. First answer, come to the presentation by Daniel tomorrow.
Yeah, basically I'm working on raster data cubes for DGGS.
Yeah, and second answer is that I think it's also in the rest of my presentation is that we are still building part of much of the infrastructure before this becomes a full-fledged GIS, and that's one of the pieces of the puzzle that is still in development, as it were.
I mean,
for instance, Google Earth Engine stores imagery in their original contracts.
Yeah.
So it has a different file format, so it transforms images, but it doesn't reshuffle them, right? It doesn't regrid them or warp them or anything. So any operations you do, the rewarping is done fly, and the S2 is basically used as a spatial index.
Okay.
Quickly find.
Yeah, right.
Yeah, but it also depends a lot on which grid you're using. For instance, if you have an easy hierarchization of your cells, then you can scale it in a logarithmic way, the way you query the points. And instead, if you have more geometries checks to do, like the rays test or summing the angles, those often require trigonometric operations that are more time consuming. So yeah, I think it depends a lot on the grid.
Okay, I will then move on to the closing bit of this session. So I hope this all sparked a bit of your curiosity. So now the rest of the slide is what you do next, okay, after this. So if you never heard of it, you can also start by reading. You know, this was all very at the surface, and you can read a bit better and study the theory and how this got here. And I have here a few links to places where you can read more about DGGS and how they came to be what they are now. And then the tools, okay? We have DigiGrid, the granddaddy of all this. And for DigiGrid, you have different bindings in different languages. For instance, DigiGrid R. It's very old. I used it for many years to do this kind of exercise that Davide showed, spatial stratification. There's also a little bridge for Python. There's the implementation in Julia that Daniel will be showing tomorrow. XDGGS, again, coming to this domain of arrays. There's also the Uber H3 library out there with also different bindings for different languages. And DGGAL. DGGAL is the most recent of these libraries, and it's kind of state of the art. So it re-implemented a number of things such as the Snyder projection with improvements. So it corrected some errors, etc. So that's the state of the art at the moment. And another new thing is A5. So this is based on some weird pentagons, roaming pentagons, but it's quite an interesting curiosity, I would say. So there's plenty of tools out there to try. And then if you want to code, if you want to get really involved and help bringing this to the future, you can join us in this project called GeoPlagma. This project started a few months ago after a chat I had with Davide, and then eventually Daniel and other folks joined. And in a nutshell, what is this project about? There are two essential goals here. One is to understand that we have all these tools and they work in a slightly different way. And we want to have a single, let's call it a single API, a single interface to all these tools. Okay, so that's the first goal. And the second goal is that this becomes the bedrock on which you can build a new generation of geographic information systems. Okay, since the DGGS is a reference system, you have to start from scratch. Like it's like you want to do a GIS, but you don't have Proj. Right? If you don't have Proj, you can't do anything, right? So we have, imagine that you have now a different kind of Proj and you have to build everything else on top of it, right? That's the long-term ambition of this project. And if you're interested in this topic and if you want to participate and develop things, I invite you to join us. So there are a few slides about this. I won't go too much. So this project is being developed in Rust. It's called GeoPlagma, 2 Greek words, earth and grid. And also, we don't want this project to exist in isolation. We want it to be an aggregation point, also a gateway to the emerging libraries. And community. Community is key to any project like this, all right? Of course, and we are talking here about open source, we are in the science domain. This is just a glimpse of the institutions involved at the moment. So most of them in Europe, but also in Australia and Canada. And basically, these are the folks in this little network trying to progress in this realm. So tomorrow at 15:30, here in the same room, we have Daniel Laws. He will be going into this topic again from the Julia perspective, and also in the direction of in this case data cubes, so gridded data. And well, I will be there, and I hope you too. Thank you very much, and enjoy your life.